Hi everyone, I'm Yangling from Aqualab APFL. I'm here today to present our latest work on spiking neural networks for active time-resolved SPAD imaging. First, I will talk about what is the SPAD and why spiking neural network is promising for SPAD signal processing. Then I'm going to formulate the problem that we need to solve when using SNNs for SPADs. SPAD is basically a p-n junction reverse biased over the breakdown voltage. When a photon hits the depletion region, it may create an electron-hole pair and trigger the avalanche breakdown. Therefore, a pulse in the voltage signifies the detection of a single photon. Besides, the buildup of the avalanche breakdown is ultra-fast, which enables the precise timing of photon arrivals and facilitates time-resolved imaging. SPADs has gained wide applications that are using LiDAR for 3D imaging, in flame for biological and medical research, and PET for cancer diagnosis, and in many other applications. In recent years, SPADs also come to consumer electronics. If you have an iPhone 12 Pro or newer models, you are carrying a SPAD sensor every day, which is part of the LiDAR system in the iPhone. In Apple's mixed reality glasses, the Vision Pro, there is also a LiDAR system. The core technology behind them is a SPAD sensor from Sony, which is made available for other devices at low cost this year. Apart from Sony, Canon announced the first interchangeable lens camera with a SPAD sensor earlier this year, which is designed to capture subjects in extremely low light. These sensors offer new opportunities and challenges for computer vision systems and algorithms. The figure below shows how traditional time-resolved SPAD imaging works. A pulse laser is used to illuminate the object, and the SPAD detects reflection or emission light from the object. Both the detection signal from SPAD and the reference signal from laser are sent to TDC, time-to-digital converter, for timestamping. Then the timestamps are histogrammed and processed. However, a lot of data are created in this process, and it lays great burden on data transfer, storage, and processing. Therefore, we consider implementing neural networks near or even in the sensor to realize high energy efficiency, low latency, smart, and real-time imaging. And spiking neural networks are a natural choice here, considering that the output of SPAD is spikes, while the input of a spiking neural network is spikes as well. With spiking neural network in the sensor, we can eliminate histogramming and even time-to-digital converters. However, there are a lot of challenges using SNNs for SPAD. SNNs themselves are notorious for the difficulty of training, and there are challenges for SPAD signal processing as well. The figure on the right shows two straightforward ways to use SNN for SPADs. We can take the reference and detection or the sum of them as input directly. One problem here is that you can see a lot of blank repetition periods where there is no detection signal. This blank repetition periods lengthen the sequence. To get high temporal resolution and enough signals for processing, millions of time steps are required, which reduces the energy efficiency and, what's worse, creates the gradient exploding diminishing problem during the training. This blank repetition periods also change the spike density, which poses a bigger challenge for SNNs. It would be easy to transform these spike trains into more informative ones on the PC, but the hardware limits such flexibility. Herein, we hope to build a general spiking neural network framework with hardware feasible encoder that transforms the phase-coded spike trains, and we need to find the tailored training methods to effectively train the neural networks. So in this work, we propose two methods, Transporter SNN and the Reversed Start-stop SNN. I will talk about the architecture that they share in common and then delve into respective designs. We adopt a simplified leak integrate and fire model as the spiking neuron here. It features a linear decay, hard sub resets, and weighing sum inputs. Such a model can be implemented on the hardware easily. The weighted sum can be implemented with the lookup table since the input is binary. The decay can be implemented with an adder, and the reset can be implemented with an adder and a comparator. It is worth noting that no multipliers are needed here compared to artificial neurons. As our first attempt to explore the spiking neural networks in this way, only one or two hidden layer fully connected neural networks are used. The output is decoded as the average firing rate, and mean absolute percentage error is used as the loss function. Then we come to the first method, Transporter SNN. The core idea behind the Transporter SNN is a ring oscillator-based structure that is synchronized with the laser signal. The detection signal is injected into a ring oscillator and keeps circulating until the acquisition is completed. Since the period of the ring oscillator is the same as the laser, the relative distance between detection signal is preserved. The ring oscillator actually folds multiple repetition periods into one, reducing the sequence length from millions to thousands or even hundreds. The phase-coded spike trains are transformed into density-coded ones, which facilitated the training of the SNNs. Since the sequence is only hundreds or thousands of time steps, we can train the SNN directly using backpropagation through time with surrogate gradient. The second method is the reversed start-stop SNN. The core idea is to use a flip-flop to enable and disable the SNN as a whole. When a detection signal is received, the SNN gets an input and is enabled. The membrane potential starts decaying. When the next reference signal is received, the SNN is disabled and the membrane potential stops decaying. With such an architecture, the phase-coded spike trains are transformed into interspike-interval-coded ones, and all the blank repetition periods are skipped. And one important feature that it brings is that the average arrival time of photons is proportional to the inverse of the count rate, which facilitates the training afterwards. Even though the blank repetition periods are skipped by the flip-flop, the spike trains are still too long to train from scratch. We come up with using AN to SN conversion to pre-train the neural network. The principle is that an integrated firing model with rate coding is equivalent to an artificial neuron with regular activation. So we can train on AN first, convert it to SNN, then fine-tune it with the BPTT and the surrogate gradient. We train and evaluate the proposed SNNs on a traditional active time result SPAD imaging task, fluorescence lifetime imaging. Here's the visualization of the encoding of spikes. On the left is the density encoding of Transporter SNN. The timestamp is subject to an exponential distribution. The shorter the lifetime, the higher probability that you get a smaller timestamp. On the right is the interspike-interval encoding of Reversed Start-stop SNN. The spikes are generated by a Poisson process. The longer the lifetime, the denser the spikes. You can see the firing rate increases linearly with the lifetime. Compare this to encodings, you can see the encoding of the Reversed Start-stop SNN has much more time steps than Transporter SNN. We use a synthetic film dataset for the training, converting timestamps into spike trains, and we train and evaluate the SNN on various levels of background noise. One classic method, central mass method, and one method we proposed before, the long short-term memory, are benchmarked here. One can see that the LSTM performs very well in all noise levels. This is understandable because the LSTM has much more parameters in a complex architecture. The Transporter SNN outperforms the CMM in the presence of the background noise. The evaluation of the Reversed Start-stop SNN is kind of different due to its unique encoding. Nevertheless, it shows robustness in different noise levels and outperforms the CMM in the presence of background noise. It would be interesting to look into the firing pattern of the spiking neurons. Here shows the heat map of the firing of the first hidden layer of the Transporter SNN. Most of the input spikes are fired between 100 to 300 time steps, so you can see an increase in the firing among a lot of neurons. You can also find some neurons firing less within this range, such as neurons 6 and 7. This behavior mimics the excitatory and the prohibitory effect in the biological neural networks. Besides, we can also see some neurons that never fire, which are the dead neuron that can be removed from the network for simplification. In the end, we also tested proposed SNNs on experimental data, where timestamps are converted into spike trains as well. The sample includes some fluorescent beads with different lifetimes. We can see that the prediction of the SNNs are inconsistency with the benchmarks, showcasing the potential of integration of these SNNs into real film systems. In the future, we plan to extend this work in two directions. On the software level, we plan to explore the SNNs with more complex topologies in the neuronal dynamics, and we also plan to extend these SNNs for other applications such as LiDAR-based object detection. On the hardware level, we plan to design sensor SNNs and integrate them into SPAD sensors and use them for the real flame or LiDAR systems. That's all of this presentation. If you have any further questions or look for collaboration, feel free to contact us. Thanks for your attention.